Alrighty, so we're going to take a couple minutes to discuss how we account for the vapor pressure of water when we're looking at a reaction that occurs in the presence of aqueous reactants or aqueous products. So I call this section reactions over water, but it's super common. Most of the stuff that we work with in the lab is aqueous. So when you're trying to figure out the partial pressure of the water, there's tables, they're readily available online, and the partial pressure of the water is going to be a function of the temperature. So dependent upon the temperature. And we'll use the table then to figure out the partial pressure of water at 25 degrees Celsius. In addition, we're going to use Dalton's law of partial pressures. This is just another example of Dalton's law of partial pressures. The total pressure that's measured is going to equal the partial pressure of the water. And in this case, we're going to look at the reaction, but only hydrogen gas is produced. So it's just the sum of these two gases. However, if you're dealing with a system that maybe two gaseous products are produced, then you would want to do the partial pressure of the water plus the partial pressure of all the other gases in your system. Our total pressure, so what you measured coming out was 747 millimeters of mercury. And looking at my table, at 25 degrees Celsius, water has a partial pressure of 23.8 millimeters of mercury. And then the only other gas in the system is the hydrogen gas. So the remaining pressure must be due to that hydrogen gas. So when I subtract it, I got a partial pressure for the hydrogen gas equal to 723.2 millimeters of mercury. Alrighty, so I erased what we had previously, rewrote it, and then converted it to ATMs because we're going to have to use, surprise, surprise, we're going to have to use the ideal gas law here. So the next thing we really do need to do though is come up with a balanced equation for the reaction. So we have magnesium metal, so I'll do Mg solid plus we have excess hydrochloric acid, so HCl aqueous. And then this is going to be a single displacement reaction, right? We really should be looking at the activity series to make sure this happens. However, I've done this enough in lab to know that magnesium metal readily reacts with acid. So H plus and Cl minus right here. And I'm thinking about what goes on with magnesium. I would do 2 plus because of its location on the periodic table. So remember with your single displacement reactions, if they do involve an acid, then hydrogen gas is going to be produced. But even if you forgot that, they're being kind. They told us that's one of the products. So hydrogen is produced along with the magnesium loses electrons, becomes magnesium 2 plus, and then it's going to combine with that chloride ion, and we're going to get magnesium chloride, which is aqueous. It's important to know that this is aqueous, right? Because otherwise we would have to, if it was gaseous, we'd have to account for its contribution to the total pressure somehow. Alrighty, continuing from there, this isn't balanced, so we'll balance that real quick. We need to figure out how many grams of magnesium metal are used in the reaction. However, they give us a lot of information about the hydrogen gas. We have the volume of the hydrogen gas, and we were able to figure out the pressure of the hydrogen gas, and we're given a temperature for the system. So given those variables, I know I can solve for moles. So I'm going to do N equals PV over RT. So I'm going to plug in the 0. I just kept a bunch extra sig figs there. I'm going to plug in that pressure times the volume, which is 3.557 liters, divided by R times T. So T I need to convert to Kelvin. R is known, right? It's a constant. So 298.15 Kelvin. Let's see how things are canceling. So we're going to have liters for sure canceling. Atmospheres is gone. Kelvins is gone. Moles is on the bottom. Moles flips up. So the units work out perfectly. When I did this earlier, I got a value of 0.138345 moles of hydrogen gas. Now, since we have a balanced equation, we can use the moles of hydrogen gas in conjunction with the mole-to-mole ratios. So I'm going to start with the 0.138345 moles of H2. Again, I'm just keeping a bunch of extra digits till the end. So 1 to 1 with our magnesium. So 1 mole of H2 needs 1 mole of magnesium. And since they asked me for grams, I'm going to tack on the molar mass. I use 24.305 grams. Moles cancel, moles of hydrogen's canceling, and I'm just left with grams of magnesium. So I obtained a value, very reasonable, 3.36 grams of magnesium metal. Such a cool problem. So many different little things going on here. The first thing that I noticed was that the reaction occurs over water. And eventually they asked me, what is the total volume of hydrogen gas that's collected? I did also take note of the fact that hydrogen gas is the only gas in the system besides the water vapor. So we can say that the total pressure of the gases equals the partial pressure of the hydrogen gas plus the partial pressure of the water. So I did 744 millimeters of mercury, and then when I went to my chart, I found that at 35 degrees Celsius, water will have a partial pressure of 41.2 millimeters of mercury. So therefore, the partial pressure of the hydrogen gas will be equal to 702.8 millimeters of mercury. I divided by 760 and found the partial pressure of the hydrogen gas in atmospheres. So 0.924737 atmospheres. Just getting ready for my ideal gas law, right? Alright, what else did they give us? What else can we say? Put that to the side for a second. So it's interesting. In this problem, they give us the mass of the solid. It's almost like a reverse of the previous one. So I know that if I know the grams of aluminum, I can go to moles of aluminum. And using the coefficients of the balanced equation, which they gave us, I can get moles of hydrogen gas. So let me go ahead and do that. So 1.65 grams of aluminum and 1 mole of aluminum has 26.98 grams. Now I want to get rid of moles of aluminum, so I'll do 2 moles of aluminum per 3 moles of hydrogen gas. And that's good because at this point then I'll have my N. I got 0.09173 moles of hydrogen gas. We have the partial pressure of the hydrogen, the moles of hydrogen. We have a temperature, it needs to be converted to Kelvin. And that's it, that's enough, right? We can solve for moles with that. Oh, we're not solving for moles. We can solve for volume with that, right? So PV equals nRT. And we're solving for the volume of the hydrogen gas. So I'm going to do volume equals nRT over P. So I'll plug in the moles that I just got, the 0.09173 moles R, and temperature. When I convert it over to Kelvin, my temperature wound up being 308.15 Kelvin. Big set of parentheses around the top. And then make sure you're grabbing that correct partial pressure, right? You just want to account for the hydrogen. You don't want to have the water in there as well. So 0.924737 ATMs. Atmospheres does not cancel out. Let's see. Moles cancels. Kelvins cancel. And I'm sorry, atmospheres does cancel right there. And we're just left with liters. And so at the end of the day, I got, again, all these answers seem super reasonable to me, that we would have a volume of hydrogen equal to 2.51 liters.